Welcome to the pre-recording of Lecture 8 of MCS 481, a course in computational geometry. So today we are in the third week of the semester and we are closing the third chapter in our textbook. So the goal of the course is that the textbook becomes accessible, that you can read the textbook. Another goal and is also that you can compute. So this is a course on our computational track. So I will start with CGAL and then indicate how for a monotone polygon there is an algorithm to triangulate the monotone polygon in linear time. So that is the main result of this lecture. All right, so we are using CGAL, and in the previous lecture we have kind of neglected this. I hope to make up for this. So what we considered in the previous lecture was the partitioning of a non-convex polygon into monotone pieces. And I will give the definition and in the next slide. So this lecture is still more or less self-contained, even though it is the end of our third week and the end of the third chapter. So if we look at the documentation of CGAL, then actually the sweep line algorithm of our textbook is implemented in this function, y-monotone partition 2. So that takes a polygon that is not y-monotone and it breaks it up into pieces that are monotone. So that's the first stage. And then in the second stage, and this is the part that we are going to consider today, the monotone pieces are actually partitions. Then we can run triangulations. So this is the finest grained description of the algorithms. So in the previous lecture we considered an n log n algorithm for computing a monotone partition. When we program, we can program in C++. So the bottom line here, CGAL is written in C++, but there are swig bindings, and these are fairly recent. So one can also construct partitions in Python, and also triangulations in Python. Okay, so let me back up a little bit what I have just said. So here you see the documentation of the monotone partitioning, and let me quickly adjust the user manual a little bit. Not the user manual, but the layout. So to the partitioning, and I will indicate where I copied this from. So here you see the monotone partitioning, and highlighting here the reference 1. So I'm highlighting the sentence, what happens for producing a y-monotone partition. The sweep line algorithm presented in 1 is implemented, and 1 is the one reference in this course. It is our textbook. So it also states the main results of the last lecture, n log n time and linear space. Then it gives an example on convex partitioning. So this is the CGAL documentation. There is the CGAL triangulation. So I will illustrate the swig bindings for Python programmers. And here is the relevant documentation. So I should actually say we have not really defined in precisely as mathematicians what is a triangulation of a polygon. Well, it's a collection of non-overlapping triangles whose union is the complete polygon. So that is the definition of a triangle, of a triangulation. So this documentation here, this documentation page, I will refer to it when we get to the triangulation _2 in the Python swig bindings. So Python, for mostly the people on the computational track, that was our main language. People who have studied data structures did this in C++. And here I'm going to the relevant page um, in the source code for CGAL. So there are the examples. So there is the partition _2 examples, and that illustrates the making of a polygon and then also the y-monotone partition. So C++ can be very complicated and cumbersome, but CGAL actually has provided extremely useful wrappers. So you see that essentially the C++ program is also not that uh, complicated, not that inconveniently long, I should say. Okay, so that's a first detour, a first introduction. So let me go back to um, the Jupyter Lab environment that I'm using here. So there is the Python code. So I'm actually still terminal person. I'm using the .py script here. So here you see the Python scripts with the code. So I have a list of points. So a point _2 is an abstraction provided by CGAL, and we are going to use the triangulation _2. So what that will do is it will consider the convex hull of the points, and you should see this as the base of a pyramid. So the construction that is useful here is this construction here, as explained on this documentation. So we will have infinite, so we have a point at infinity, so that's actually the top of the pyramid. If that top is high enough, so it's here shown, of course it's a finite pyramid, but it should be considered as a point at infinity. So that ensures that the subdivision is a triangulation. So subdivision of a polygon is a subdivision in cells where the cells do not overlap, and the union of all cells is again the entire polygon. A triangulation is a particular subdivision where all the cells are triangles, and that is accomplished by using this construction here where we have this face at infinity, this vertex at infinity. So this makes that, so the script is actually quite short, as you can see. So we can enumerate all the, if we insert the points into the triangulation object. So we make first a triangulation for the two-dimensional collection of points. We can ask for the number of faces and actually the number of vertices. So there is still a bug in this. So let me just fix this real quick, and also save this. So I will run the script. So you have the test for all edges. I only want to see the finite edges. I only want to see the finite faces. So every face is a triangle. Um, okay, so let me now run this. So I practiced this. Um, here you see, oops, number of vertices. Ah, this is embarrassing. So here we go. Um, you see the script. It's well designed. Everything fits in one terminal output. So we have 8 vertices on input. We get 8 faces and 8 vertices. So that's why I didn't really notice this bug. So you have the 8 finite faces. So the points are given so the edges are given by 4 numbers, the coordinates of the beginning and beginning and the end point. The faces are triangles, so you have the vertices so you have 6 numbers, the 2 coordinates of the edges. Okay, so in some sense, this is if you have to make a triangulation of a polygon, and if you are a Python programmer, then this is the fastest way to do this. So it took me a while to figure this out with the documentation of CGAL, the examples in the swig bindings. So here you see the more proper way of working now with a Jupyter notebook. Both the Jupyter notebook and the Python script will be made available at the course website. So we can also hear there is something more in this, so we can ask for the string representation of all the points. So we have the 8 vertices. And here I have printed out also the infinite edges. But there are 15 finite edges. So then we have also the infinite faces. Okay, so that's the brief introduction to the CGAL perspective in this course. Going back to the background for this single slide in this lecture. All right, this also provides the context with the connection with the previous lecture. Okay, so let me now consider what is again now a y-monotone polygon. Well, if you consider a horizontal line, then this horizontal line intersected with the polygon is either empty, one vertex, or a line segment, or in any case, it's always connected. So we are extending that definition or making a little bit more restrictive. We actually do not want horizontal edges. So if you could also actually argue that if you have horizontal edges, well, it still is y-monotone, but actually you have then essentially a partition. So you have 3 edges, but the 3 edges actually are connected. So they all line up. So you have collinear edges. So for the simplicity, we will assume that the polygons are strictly monotone. If you're wondering about an example that is not y-monotone, well, think about the Christmas tree. So it's still summer here, so it's a little bit strange to think about Christmas trees, but if you draw a Christmas tree, then you will not have a y-monotone polygon. All right, so this is our input, strictly y-monotone polygon. I will use this as our running example to illustrate the algorithms. The last exercise will ask you to consider a polygon that is not strictly y-monotone and see what needs to be modified for that. All right, here is an algorithm. So we can work recursively, divide and conquer. So what we do is we kind of have our polygon that is strictly y-monotone, and we consider the leftmost vertex. We add a diagonal, and then actually we separate that. So you can see that this algorithm will actually terminate. So each time when we remove, after adding a diagonal, if we remove the new triangle, we still have a polygon that is strictly y-monotone. So we proceed in that way. So we take the highest leftmost vertex, that is our vertex V. And then we try to connect the neighbors U and V. So that goes well for the top leftmost vertex. Also works well in the second step. So also goes well there. But then you see there is this next step when V is on top here. U and V cannot be connected because we have to consider, so if you connect U and V, the two U and W, the triangle, I'm sorry, so we have V is our leftmost top vertex. U is the vertex that is connecting, and W is the other one. So if we would have the triangle spanned by U, V, and W in this case, then actually the triangle would not be strictly inside our polygon. So we have to connect V to the vertex that is farthest away from that diagonal. So we have a diagonal that doesn't lie in the polygon. So we cannot use that diagonal to separate, to split off a triangle from our polygon. Instead, we take the point that is farthest to the left. So from the farthest from the left from that diagonal. So we know what is the top. U is the top here, and we go to the left, to the farthest most. The fact that this is farthest to the left will make that the diagonal of U and of that farthest most point is now inside, and that's a triangle that we then can split off. But of course, you see that we also have then the V, and becomes actually the W. So there are things that are kind of still tricky with this first recursive algorithm. All right, do you see it? Let me first or immediately say that this was a first approach, and that's kind of a first idea. But the idea, even if we are optimistically, it could lead to a quadratic algorithm. So in the worst case here, what we may have is that every diagonal cuts. So optimistically, we would have indeed a divide and conquer. But actually what was already a little bit clear from the previous example is that we would only cut off one vertex at a time. So that would mean that we have a double loop. So we have the vertices that we cut off. And then actually we always need to add diagonals. So actually we still have n-1 steps to go. Um, so that first idea is actually not really good. All right, we will assume the fact that we have a convenient representation for our y-monotone polygon. So if we don't have this, we will sort the vertices and make sure that there is an order in this polygon. So here is actually the idea. The fact that the polygon is y-monotone means that we can talk about a left and a right. So if, again, what is y-monotone? Do an intersection by a horizontal line and there is only one segment at most. Could be empty as well. So that was the idea that we used for the sweep line algorithm. So that means that there is a left and a right. So what we will exploit here is that we can try to connect points from the left and the right. This slide also serves as another illustration of the doubly connected edge list that we have been using, that we have defined earlier. So in particular, we have here 8 vertices, so they are connected by edges. So the edges are represented actually twice as vectors. So every vector, every edge is actually a half edge, and it has a twin. It depends whether you then traverse the convex hull, or if you, I'm sorry, shouldn't say convex hull, but whether you traverse the polygon in counterclockwise or in clockwise order. So we have two faces, an inner and an outer face, 16 half-edge records. And the triangulation will also be stored in a doubly connected edge list. So we will actually update, our algorithm will update this input data structure. Okay, here is now the idea. So if we have a polygon that is strictly monotone, then actually we have no horizontal edges. That means that there is a very strict order. So we can look at the polygon as we can partition the vertices in the polygon by the left and the right boundary chain. And we will add diagonals. And we have to ensure, of course, if we are at diagonal, that everything lies properly in the polygon. And to determine this, we define the notion of a convex vertex. A vertex is convex if the inner angle is less than 180 degrees. So perhaps I should make the drawing now. So we have a convex vertex V here. So the angle is less. We have a reflex vertex. A reflex vertex is over here. So the inner angle is here more than 180 degrees. So our monotone polygon is not necessarily convex. And I should have pointed this out earlier. Triangulating or convex polygon is very straightforward, can be done in linear time. And that's actually here the algorithm again, so that's the point here. Okay, we have two types of vertices. And why is this important? Well, let's start the algorithm. Let's just do it. How can this be so bad? Okay, we are running to the example, and you see that 2 and 3 are at the same height. So that means that we can add a diagonal. So you don't need to worry about this. Then we add 3 and 4, 4 and 5, 5 and 6, 7, and actually we do have a triangulation already. But what's the problem here? We have two reflex vertices. And they actually have no problems here. So here you can see that if the algorithm proceeds in this way, with the invariant that the highest leftmost vertex is convex, then we have no problem. So this example is thus done. All right, what can go wrong? Okay, so suppose that we have sequences of vertices. So we have a sequence of reflex vertices. So the 5 is on the left boundary, the 1, 2, 3, and 4. You see that the inner angles are all more than 180 degrees. So if we start adding diagonals, and actually we can only start to add diagonals when actually we get to the fifth vertex. And how can we do this? Well, store the reflex vertices on the in a stack. So if we have walking on a chain and all the vertices are reflex vertices, then we at the time when we are at the fifth vertex, we can actually start popping from the stack and add diagonals. Okay, now we do have the algorithm. So we're going to merging vertices. Um, we have our topmost vertex, and we start walking and we merge the left and the right chains, and we are uh, doing this merge of the vertices starting from the top all the way to the bottom. So we push onto the stack our first two vertices, and then we process them. We process the vertices one after the other. So we have one outer loop already. So how do we process the vertices now? We check whether the top of the stack and the current vertex. So this is stepwise refinement. So the processing is of the previous slide is actually done here with the statements 4 to 9, and you see there is also an else. We will pop if we are on the opposite change. If they are on the opposite change, then this is the example that we had where the 5 and the 1, 2, 3, 4, if they are opposite, then we can start inserting diagonals. Okay, the correctness proof is important here. So the first exercise asks to explain why the diagonals that are inserted will be inside the polygon. So let me try to refer to the examples here. So we are processing the points in order in their height, and it's only when we have a point at the opposite chain that we can process it. So if we think about here, so we are processing the points. So 1 and 2 have been added. So we are now at point 3. So if you look at statement, so the top of the stack are thus far not on, so the whole chain is still the sequence of points here. So O3 is not, and U4 is also not. It's only when we are at the fifth that the fifth point and the top on the stack here is actually on opposite chains. So the U sequence is the sequence of points that we are processing. Topmost, left topmost points first, or topmost in height. So when we come to U5, the top of the stack is actually 4, and at that point U4, and actually we can add the diagonals. We do this except for point 1, so we keep the bottom. Okay, so we also popping 1 then. So in the exercise, you have to explain why the diagonals are inside. And in that proof, you have to refer to the definition of the y-monotonicity. So you can argue with contraposition, assume that the diagonal would not be inside. That wouldn't lead to a contradiction, that the polygon was not y-monotone. Also, the processing order of the vertices is important. So there are these two facts that you have to take into account. Okay, so we are processing vertices. So we have the first case, and then we have the second case. So how do we process vertices on the same chain? So here you see that on the same chain, actually we are not going to insert any diagonals, only at the very end. So the second exercise is will then lead to the correctness. So in step 17, you add another diagonal. And also here you have to show that this added diagonal lies strictly inside the polygon. So when we process vertices on the same chain, we check whether the diagonals are there, and we actually are updating now. I'm sorry, I said something wrong here. So we are actually inserting, we are modifying the doubly connected edge list that represented the input. So we are actually inserting diagonals. Okay, so this is concluding the algorithm. So we have the insert of the diagonal that we do both in the when they are on opposite chains. Um, Here is the other case. So when they are not on opposite chains, then we have to make sure that vertices that are on the same chain, we actually are checking that the we are we can do this when we don't have reflex vertices. So the test here will essentially test the angles. Okay, a picture here is also in order when you are solving this exercise. Okay, so I have about 15 minutes left now for the cost analysis. We're going now through the algorithm step by step and making sure that our cost analysis will remain linear in the number of vertices. Okay, what was our initialization? We are going to process the vertices according to the height, merging the left and the right chains. So the merge sort, this merging of two sorted lists takes linear time. So that's a result that you have seen from data structures. From data structures, we will also work with stacks. So stacks are very useful for reverting um, the order, and we needed the stack. Stack was a quite convenient um, data structure for adding diagonals from opposite chains. All right, now we have the critical part of the cost analysis. So we have the outer loop executed minus 3 times. However, we have two inner loops. And that is troublesome or worrisome because we may run into a potential quadratic running time. Okay, no, and it's also the if-else statement here. You cannot get away with the fact that we have to consider that both inner loops can be executed. Okay, so let us look at the stack. So the stack, how large can it ever get? Well, let's count the operation. So the stack size, so we look at the push operations in the code. Uh, there can be at most two push operations per step. So the stack can actually never grow quadratically. So, and that is also a number of bounds on the number of pops. So if you have to consider, so for all the U's that are in the stack, then actually that stack is the number of pop operations. So the total number of times you can actually run this, even if it is an inside a double loop, you can actually only do this in total 2n minus 4 times in total. So inclusive the outer for loop and also the inner for loop. Okay, so therefore we do have the main theorem. So if you have a monotone polygon, then it takes linear time to triangulate this. If we are working with a doubly connected edge list. So the doubly connected edge list gives a very convenient representation for the left and the right boundary, which makes the merging of the two lists of vertices linearly. The stack takes care of the adding of the diagonal elements on the opposite sides. Okay, the last exercise deals with monotone polygons that are not strict y-monotone. That means that there are horizontal edges. There is a very quick way to deal with that. That's to use an epsilon perturbation and see what happens there. Another way to deal with this, and probably the best, more slower way to deal with this, would be to look at the example here to the right and see what happens when you run the algorithm on this side, on this example. So that would be the beginning for this exercise. All right, we have finished the third chapter. This is lecture 8, and it's only the second lecture that I'm explicitly using CGAL. I hope that to remedy this in also the next lectures and in our computer project that is still following. I hope that CGAL is large and that it does not overwhelm too much. Run the examples that are provided with this lecture. Look at the documentation. I will collect homework exercises, a selection of homework exercises. The exercises on the slides are meant to slow you down a little bit when you look at the when you try to digest the material. The goal of the lectures is actually that you can read the textbook. So the textbook also has exercises, and you also good activity is also to look at these exercises.